All right, so the last video we looked at the differential rate law, which we just call the rate law. And so this is the first example in your notes. You'll see the chemical equation here is 2NO plus Cl2 yields 2NoCl. So I want to run through this example with you. There's typically 3 parts that you will need to complete for this type of problem. The first step is to write the form of the rate law. So remember, we're using method of initial rates, so we can ignore the products. So the form of the rate law for this one is rate is equal to K, your rate constant, and then it's times the concentration of the first reactant, NO. Now remember, in the rate law, the exponents have to be determined from the experimental data we have down here. So we're going to define right now the exponents in terms of X, Y, and Z. In this case, X and Y. So to the X power times concentration of the second reactant, Cl2, to the Y power. So here we have 2 orders we're going to be solving for. Now, again, we're using method of initial rates. So the first example I'm going to do for you is I'm going to do it sort of a longer way, and then from then on out I will do it a shorter way, because the longer way is just to show you how certain things will always cancel out with the method we're using. So what you want to do is you want to try to find the order for the NO and then the order for the Cl2 separately. So you want to find a situation where the concentration of the NO is changing, like in experiment 1 and 3. So I'm going to put an asterisk here and here. But this is constant here, and then it's changing here with the Cl2. So pick it where one of the reactants concentrations is constant and the other is changing. So it's constant here and it's changing here. So we're going to use experiment 3 and 1, and I'm going to put experiment 3 over experiment 1 because you want to make sure the larger numbers are on top. It just makes it work out more nicely. So I'm going to use experiment 3 over experiment 1. Now this is, again, for the first one, I'm going to show you the longer way to do it. So I'm going to take this rate expression, we're going to make a ratio with it. So rate of experiment 3 equals K of experiment 3 times concentration of NO to the X power times concentration of Cl2 to the Y power. And you're going to make a ratio with that. So it's over the rate of experiment 1 equals K of experiment 1 times concentration of NO to the X times concentration of Cl2 to the Y. So let's plug in for our values here. Come over here for experiment 3 and plug in your rate, 2.86 times 10 to the negative 6 over experiment 1's rate, 1.43 times 10 to the negative 6 equals K. Now, for experiment 3, you're going to plug in the concentration of NO, which is 0.250 to the X, and then you're going to plug in the concentration of the Cl2 for experiment 3, 0.500. Keep in mind these are molarity. And you're going to do the same thing with experiment 1's. So the K for 1. Now plug in the concentration for the NO for experiment 1, 0.250 to the X times 0.250 to the Y. Now what you will see is the reason we picked a situation where 2 of the concentrations were the same and only one of the concentrations was changing is because we need some things to cancel out to simplify the calculation. So you'll notice since K's are constants, they always cancel out. So the K always cancels. And here, this part will cancel out because that's identical. So we can bring down what is left over. I'm going to go ahead and do the math. 2.86 times 10 to the negative 6 divided by 1.43 times 10 to the negative 6 reduces to 2.00 equals, now 0.5 divided by 0.25. That's equal to 2.00 to the Y power. Since both of these are raised to the same exponent power, you can just divide and raise them to the y power. Now, for this one, this is actually a perfect square. Sometimes if it's not, you might have to use left, right, center. But you can tell from this one that 2 raised to the first power equals 2. So that means in this case, y is equal to 1. So that's the order with respect to the y. And now we're going to do the same thing. We're going to solve now for the exponent x. So for that one, you want to find a situation where the NO is changing, but the Cl2 is constant. So I'm going to choose experiment. Notice it's constant here for the chlorine, and it's changing here for the NO. So I'm going to use experiment 3 and 4. And again, I need to put my larger numbers on top to make my numbers work out easier. So I'm going to put experiment 4 over experiment 3. Okay, so I'm going to just say rate of 4 over rate of 3 equals. Now, since the k's always cancel because they're constants, the other thing that will cancel is the one that's staying the same. So in this case, the Cl2 is exactly the same. It will cancel. So I just need to worry about the concentration of the NO. So I'm going to plug in concentration of NO to the x power to the y power. I'm sorry, to the x power here. All right, so that was plug in. Rate of 4, plug it in here, 1.14 times 10 to the negative 5, divided by 2.86 times 10 to the negative 6. And the concentration of NO is 0.500 in experiment 4 and 0.250 in experiment 3. That's all raised to the x power. You divide this, you get 4.00 equals 2.00 to the x power. So again, this is a perfect square. And if it was not the perfect square, again, you'd have to use left, right, center. But we know that 2 squared is equal to 4. So in this case, x equals to 2. So now we have both of our orders, so we can write the actual rate law. Remember up here we wrote the form of our rate law. So now we're going to write the actual rate law. So the rate law, the final answer is rate is equal to K times concentration of NO. Now that we know the exponent for the NO is 2, that's going to be squared. Concentration of the Cl2. And we figured the y was 1, so y to the first. Now I'm going to skip on over to part 3 just to talk about the overall order for the reaction. So in this case, we had x was equal to 2 and y was equal to 1. So the overall order for the reaction is equal to 2 plus 1, which is 3. So it's a third order reaction. All right, let's come back to part 2. How would you solve for K? Now that we know our rate law, all you do is you're going to plug in, and we're going to always use experiment number 1 data when you solve for K. So rate equals K times NO squared times Cl2 to the first power. Come back up to your data table, use everything from experiment 1, plug in that data. 1.43 times 10 to the negative 6 equals K. Concentration of NO is 0.250 molar, that's squared, times concentration of the chlorine, 0.250 molar, and that's to the first power. So that's going to give you 1.43 times 10 to the negative 6 equals K. Now you're going to square this and raise that to the first and then multiply them, and that's going to give you 0.0156, and that's molarity cubed for the unit. Now you're going to divide by 0.0156 molarity cubed, and that's going to solve for K.